Welcome, everyone, to the Deep Space Dialogues. I am thrilled to be with you tonight with Dr. Klaus Pontoppidan. We're going to be here talking about the Solar System Cookbook. What is Webb revealing about how solar systems like ours came to be? Where do we come from? How do we make planets like Earth? This is a really interesting topic that I think gets a lot of people excited and is maybe a reason why a lot of people get into space in the first place. Um, so we're here to have this conversation. I do want to remind you, please subscribe to the YouTube channel as we get going so you can be notified of all the other videos that we produce here, including future Deep Space Dialogues. Without further ado, I want to introduce Klaus here. Dr. Klaus Pontoppidan has worked extensively on understanding how water and other easy to vaporize molecules make their way from ices in the interstellar medium to planetary atmospheres. He's co-leading the JDisc survey of protoplanetary disk chemistry, and he's an expert in infrared spectroscopy and instrumentation. He served as the project scientist for the James Webb Space Telescope for 8 years here at the Space Telescope Science Institute, and that included the launch and commissioning of the observatory. He also led the observing campaign that released the first color images from Webb, which have been viewed over 100 billion times. So you have definitely seen his work, whether you know it or not. Uh, so, Klaus, it's an honor to have you with us here today. And just to start off with, what has surprised you most from Webb for the past 4 years?
Thanks, Chris. It's great. It's great to be here. Um, I would say for web, I mean, there's so many things, right? It's hard to know where to start. From the point of view of the planet formation theme, right? I think that is where with web that we are in this kind of absolutely golden age I mean, we had some inkling of what we would see, but the amount of discovery space that we have uncovered with web is quite tremendous. And I think I mean, I'm a bit biased, right? I think it's almost more than with exoplanets or high redshift galaxies. I've had when I talk to people trying to compare the kind of era we're in. I've heard comparisons to when people first started to take spectra of stars and they realized, oh, there are different kinds of stars. And we have to classify them and put them into a context and try to figure out what is the physics that is behind all these different stellar types. And of course, back then it turned out, well, temperature is a big thing, right? So the different stars with different temperatures, they lead to different spectra, and that's really the reason for what we're seeing. We're doing something very similar with disks right now, and we're getting sort of a real insight into answering these questions about if whether our own solar system is common or not, and in particular in terms of what kind of planets it can make and the composition of the planets that it makes. And of course, as with always, we find that probably our own solar system is one instance of a wide range of different things that can happen.
So,
And I think we'll talk much more about all of these things, right? But
sure.
it did surprise me how many new things we're discovering about planet formation.
So one of the things I know that Webb is showing us that we haven't been able to see quite as well before is the parts of those protoplanetary disks that are making kind of terrestrial temperate worlds, right? So kind of the inner parts of the disk instead of the further out parts of the disk that telescopes like ALMA can see very well. What is Webb telling us about how water behaves in the parts of the disk that are forming rocky planets that we didn't know before?
Right. So if you're saying the disks are not what I call not monolithic simple objects, they're quite complex objects, and we've seen these amazing images from ALMA with rings and whatnot. The spatial resolution of those is such that these are really the outer parts of the disks, and planets we think form in the very innermost parts, so in areas that are not even resolved with ALMA, but we can see them and can characterize them with Webb, because what Webb sees is fairly warm stuff, actually, that is quite closely matched to this sort of room temperature gas, and that sits in disks, in planet forming disks at distances from the star of 1 or 2 times the distance of the Earth to the Sun, right? So 1 or 2 astronomical units. So that's one aspect of it. The other aspect of it is that James Webb is like a water detection machine, right? So the wavelength range that is covered by Webb, particularly by its MIRI instrument,
Hmm.
is the key region if you're interested in water, because the fingerprints of water is found there, and you can't access that from the Earth. Right? You have to be in space to see that because, well, of course, the Earth our atmosphere is a fairly wet place. There's full of water vapor in our own atmosphere, and it means so any kind of light that comes from with a fingerprint of water that gets stopped by the water in our own atmosphere. And so that's where we need to go to space with Webb, and it gives us access to those wavelengths where we can see water. And that means that we can, in any protoplanetary disk, basically, we can use Webb to measure how much water there is in the region in the disk where we think terrestrial planets are forming, or planets that later on may become habitable.
That's
So
an
thanks for
interesting
putting
point
up an
that.
image here of a disk.
Oh yeah,
Yeah,
please, yeah. Talk us through what we're seeing here
yeah.
with this disk.
This is an amazing image as well. So this is an image of an edge-on disk. So it's a protoplanetary disk that is viewed from the side, not from the top, taken with the NIRCam instrument on Webb. And it's not the only one. We have many of these now. So this is just sort of a disk that is fortuitously viewed at this angle, and it I mean, kind of it's quite extraordinary. It quite reminds me when I started out in the field in the mid '90s. Well, first of all, we didn't know that there were any planets outside our own solar system. We actually also didn't know that there were these disks, right? We had it was all a theory, right? And we thought that there might be planets and they would be formed in a disk like that, but it wasn't until sort of the mid to late '90s that there were observations with radio interferometers on the ground that allowed us to see that, well, yes, indeed, there was stuff around these very young stars. It was flattened like this, and it was rotating around the star, right? So then at that point we knew it was like, yes, there is such a thing as planet-forming disks. So
So
what you
these
see here
observations
is,
with other observatories and other wavelengths kind of paved the way for Webb, right? It took more than just one kind of instrument to make some of this science happen, right? You need
yeah,
observations from the radio all the way. Yeah.
100%. It's the classic, elephant in a bag, right? Where a disk has gas in it, it has dust, it has hot stuff, it has cold stuff, it has very hot stuff, and you can't use a single observatory to measure all those things. It has water, right? It has other other molecules, it has other elements. You need really access to pretty much the full electromagnetic spectrum to get a full view of everything that's going on. But you see a lot of it here, right? So the size of this is about the size of a solar system as we know it. There is that dark lane in the middle, sort of brownish thing. That is what we call the disk midplane. It is very dusty, and that's what you see. So the dust absorbs the light from the central parts of the system, including the star itself. You see this lightsaber kind of feature that above and below this plane. That is a fast jet that is expelled from the star so material is accreting onto the star. Is that what's called accretion? This is the star itself is still growing a little bit. It's accreting material from the star, and as part of that process, as that material smashes down into the stellar environment, some of it gets accelerated up in this very, very sharp jet, and this material moves out at very high speeds, like 100 miles a second or something like that. So it's very, very hot. It's ionized, and it emits in lines that is coming from ions, right? So atoms that have their electrons blasted off by the high heat. Then you see this blue stuff on the top here. That's partly very small grains that is lofted up to the top of the disk by turbulence in the gas. And you see a wisp sort of out down below. There's also blue stuff here. So that's probably part of a wind that's coming off the disk. So we can talk a little bit more about that later, but that's essentially how these disks ultimately dissipate. So different processes lead to a wind that is coming off the surface of the disk, and You can measure with Webb. You can measure how much is coming off, and you know sort of roughly how much mass is in the whole disk, and that means you can make an estimate of what is the lifetime. How long does it take for the disk to be just completely evaporated and dissipated? And it's a few million years, right? So the disk has a few million years to make its planets, and then the planets that this disk is almost certainly forming are probably forming within just a few pixels in the center. Right? So the scale of that planet forming region is very small.
So when we're looking at this disk, spread out on the screen, if the planets, like, in the Earth kind of distance from the star, are going to be in the first couple of pixels, is it more like the Kuiper belt that's kind of out where we're seeing the outskirts, or is it more like the Oort cloud? How far out are we seeing in this disk here?
Yeah, so it's not the Oort. The Oort cloud is hundreds of thousands of light years, right? So this is about I don't know, 100,000
AU,
AU.
yeah. Yeah.
This is about 100 AU across, or 200 AU, something like that. So the Oort cloud would be, across the room here at least. Mm-hmm. The orbit of Pluto is maybe halfway out to the edge or something like that.
So what have we learned then about the kind of Kuiper belt sort of analogues that we've seen around other stars then, if that's kind of the scales that we're probing?
So for Kuiper belt analogues, right? So for that you are off. Okay, so when we're talking about protoplanetary disks here, what that means is it means that the disk still has a lot of gas in it. It's gas rich, right? So it has sort of much of this primordial reservoir of gas. We just talked about how that gas is evaporated off the surface. It disappears over a few million years. At that point, the disk has no gas left anymore. But that doesn't mean that all the material is gone. So what this disk is very actively doing right now is forming planets, but it's also forming what we call planetesimals, which is like asteroid-sized things, maybe 10 miles across. And disks probably do this very efficiently. And those are long-lived, right? It's very hard to get rid of a 10-mile body in this disk that is orbiting at 50 AU. And so when the gas is all gone, you still have those planetesimal bodies left, and there's a lot of them, and when you start out, they tend to collide, and in those collisions, it can create sort of residual material we call debris, and Webb is really good at observing that as well, right? And so these are what we call debris disks. So essentially the material in it was what we call secondary. It's not the primordial one, it's stuff that is coming from collisions of these planetesimals. And that tells us a lot about systems that are analogous to the Kuiper belt in our own solar system, right? Because that's what a Kuiper belt is, right? It's a residual planetesimal disk from the formation of our own solar system. So whereas in our solar system, again, this gas disk only survived for a few million years, the Kuiper belt, that planetesimal disk is long-lived enough to still exist in our solar system.
So how long does it last? Do the debris disks last when you would still call it a debris disk instead of a Kuiper belt? Is that more like hundreds of millions of years, or?
Well, I mean, my opinion, every star has a debris disk. It's just a matter of how much is how big it. I mean, how much is left in it, right?
So the Kuiper belt is still a debris disk. Yeah. Okay.
Right. Our own solar system has a debris disk, and you can go and see. You can see that in not out to the Kuiper belt, but there's a debris disk from the asteroid belt, which is a 3 AU. You can see that as what's called a zodiacal light, right? So if you have access to a very dark place, and you can see it sort of a bright band that is extending up. That is our own solar debris disk. It's typically, that one is our own is like 100 to 1,000 times fainter than the famous debris disks that we have images of, that are the really beautiful ones, like the one around Beta Pig.
Like Fomalhaut or Beta Pig.
Fomalhaut, yeah. But nevertheless, in my opinion, it's still debris disk.
Yeah. So we've got kind of a continuum then, that we can take snapshots from all the way from the earliest stages of a protostar embedded with a lot of gas until it's thinning out and thinning out and thinning out until you get to more modern systems or more evolved systems like ours. Is that
right? So there's, over the lifetime of any star, there's thinning out of everything, and sometimes you can. There might be an event that stirs up all the planetesimals, right? So that can be an event that is caused by planets, or giant planets moving around. They interact with each other, and you can get this kind of unstable events that scatter that planetesimal disk and creates a lot more collisions, and suddenly you can have a brightening potentially of your debris disk, right? So it becomes a bit random sometimes also how bright a debris disk is, that we think at least.
What kind of stuff are these planetesimals made out of? I mean, we mentioned water, but can you have other kinds of molecules stuck in there on the ices? What kinds of molecules can form on there?
Right. So uh, we think that in the outer parts, so of the disk, beyond what we call the snow line.
Hmm.
The snow line is a location in a disk where temperatures are such that that water will evaporate, right? So you go just inside the snow line, things get a little hotter. The water, any kind of water ice on the grains will evaporate, and outside of that, everything is in the form of ice. Outside of that, where things are in the form of ice, we think that the amount of stuff in terms of mass between rocks, like things that you might pick up as sand on a beach, and ice, mostly water ice, but also there are things like dry ice, like carbon dioxide, and it can be other things as well, and some organic material. It's about 1 to 1 in terms of mass. And so they're dominated, those what do you call volatile things that evaporate at relatively low temperatures. They tend to be dominated by molecules that have oxygen and carbon in them. And that the amount of oxygen relative to carbon is really important. Actually, maybe I should
Please.
jump to a let's see here. This is a plot. It's one of my favorite ones, though, and I often use it to illustrate this particular point uh, in relation to the Earth. All right. So what this shows here is different elements, and it shows how much there is of this element in the sun along the x-axis relative to the Earth, which is the y-axis. So it means that if one of these elements sit on this white dashed line, it means that the Earth has about the same ratio to all the other things as is in the sun. But you'll notice that there's some things that don't fall in line, particular things like the C here over to the right, carbon,
Hmm.
is about 1,000 times less on the Earth than what's in the sun. The nitrogen is about 1,000,000 times less. So almost all the nitrogen that's in the Earth is right here around us. It's in our atmosphere, and it has molecular nitrogen. If we had received all the nitrogen that was available locally in the original solar protoplanetary disk, we would have had an atmosphere that was 1,000,000 times denser than it is of nitrogen. It would have been completely unlivable. Put it another way, if you're a random nitrogen atom somewhere in the disk, you had a 1 in a million chance to be incorporated on the Earth. Right? And the reason for that is that nitrogen, when the Earth was forming, was stuck in a molecule that is very volatile. It means it was in the gas phase where the material accreted to create the Earth, and the Earth is created out of solids. Couldn't anything that was in the gas couldn't be put into the Earth, and it was dissipated as part of this wind.
And is that mostly true of carbon as well then, since
It's
we're
mostly
also
true of
very low
carbon as
carbon?
well, yeah. And it's actually still a bit of a mystery in the Earth, because carbon can exist in many different forms, as we know, right? If carbon is in the form of carbon dioxide, it's very ethereal and volatile, right? And you have to be very cold to have a dry ice. But carbon can also exist in organics that are not very volatile at all, right? That takes very high temperatures to, like a piece of coal, right? You have to burn it in order for it to end up as a gas. So this tells us that most of the carbon that was there when the Earth was forming cannot have been in form of organic coal. That it had evaporated and burned off in some way. And we don't actually to this day quite understand why this is, and it's not it's not completely what we see in other protoplanetary disks. It's called
Have
the
we
carbon deficit problem.
have we seen carbon molecules kind of being driven off of disks by heat? Uh, in like we mentioned those winds earlier. Have we
Yeah.
seen those kind of that kind of evaporation process of carbon molecules?
We have, you can see it in carbon monoxide, for example. But another thing you do see in disks, so where we think most of the carbon is let me jump to another. We're just skipping through these. This one is a good one here. These are examples of Webb spectra of protoplanetary disks. So these basically, this is
so each line's a different star, right? Each purple line is a different disk. Right. Sorry, yeah.
Each purple line is a different disk, different system. We have hundreds of these now with Webb, and these are exquisite quality. And what they allow us to do is they allow us to do exactly what you're saying. They allow us to measure the composition of material in the terrestrial planet-forming region where habitable worlds form. So we can go with Webb and we can directly measure what is there, and we see this wide range of stuff. So if you go from the top, there are these things that are called PAHs. This stands for a long word. It stands for polycyclic aromatic hydrocarbons. We think actually much of the carbon in the universe is in this form. It is rings of carbon. That's what makes it aromatic, with
like
hydrogens.
Benzene and that kind of thing.
Like benzene, yeah, that's right. And sometimes more complicated things. But it's sort of some of the organic material can become very complex, which is some of the simpler parts of it. But we see this stuff. We see this stuff out to the edge of the universe, right? We're detecting polycyclic aromatic hydrocarbons and in galaxies that are 10 billion years old. It apparently is very easy to push the carbon into this kind of stuff, and this probably gets in disk gets lofted off with the wind. It's sort of in between a solid and a gas, but it's mostly a gas in this context, and so we see in some cases the carbon comes off in this way. So that's one explanation for how that might be lost.
So we have a question from the audience here, which I think this plot is kind of answering, which is how does Webb detect the presence of water? And I see a rotational water marked on your plot there. So you want to?
Yeah. So this is sort of this plot. So different disks as we go down actually go down in stellar mass. So in the top ones, those are high stellar mass, and bottom ones are lower stellar masses. So the two bottom ones, so the second from the bottom, that's a disk around a solar mass star, and you see all this hair in it, this little fuss. That's marked. There's one to the left is marked vibrational water, and to the right is called rotational water. All this fuss is water. That is a direct signature of water. These are hundreds of what we call water lines, so individual energy transitions in a water molecule that emits a photon at a very specific mid-infrared wavelength. And so that's how we see water, and it allows us to measure how much water there is. It allows us to measure the temperature of the water. It allows us to measure if there's different reservoirs of water at different temperatures. And we see this in almost every disk. Almost every disk we see these massive amounts of water. Now, there's an interesting point to this here. So that is that the water that we see here, you can make a model of the chemistry that is going on there. And when you do that, you find that the lifetime of this water is very short. It gets destroyed by ultraviolet photons from the central star in a few years. So
that kind of begs the question of how does water survive to end up on a planet like Earth? How do you keep it from getting destroyed?
Right. Yeah. So this is an excellent question. So once the water is in the gas like this, it gets destroyed very quickly. So it begs that question. It also begs the question of why do we see we shouldn't see any water at all? It should have been destroyed a million years.
Already be gone. Okay.
It should be totally gone. We shouldn't see any of this. In fact, before Webb and its predecessor in this context, Spitzer, came online, all models predicted there wouldn't be any water here. It would just be flat spectra. And it was a discovery that we made with Spitzer that this was quite common, and now we can measure it with great precision with Webb. we're convinced that the reason for this, that there's water now, is because it's constantly replenished. Right. So there is this process in these disks that moves massive amounts of water ice from the outer parts of the disk, where you form comets and other things, into the inner part of the disk where you form terrestrial planets. Right. And so it moves this water. There's basically a conveyor belt that is very efficient and moves ice inside the snow line, and as soon as it's inside the snow line, it evaporates, and it's pushed up into the surface where we observe it with Webb, and it's constantly replenished, because if it wasn't, we wouldn't see it. We have a pretty good idea about how that physics works. So essentially, what happens is it's almost kind of like a precipitation. So if you think of our own atmosphere, and you think of, you look up in the sky and you see there's a cloud, right? Mm-hmm. That cloud consists typically of water crystals, very, very small ones. And when they're very small, they couple to the air, right? They behave like air. That's why the cloud doesn't just fall down and smash into the ground, right? It's lofted up because there's some turbulence in the air, and you can sort of these very tiny ice particles, they stay up there until they grow, right? So when you start to grow the ice crystals in our own clouds from water vapor in the air, they grow, and at some point they grow to sizes that are big enough that they cannot be kept up anymore by the air and the turbulence, and they start to fall down, and it starts to snow, right? That's precipitation. It's a very similar thing that happens in a disk here, except it happens in 2 dimensions, right? In our atmosphere, it's just up and down, right? It just falls down. In a disk here too, that there's up and down, right? So there's that plane. So things will precipitate down, just like there's snow in our own atmosphere, but there's also an inwards direction, and that happens too. So essentially, we're seeing material snowing inwards. So what happens? Yeah, go ahead, Chris.
I was just so if stuff is moving inwards from outside, kind of drifting in, how does the presence of like a giant planet like Jupiter affect things? How do you does that change the composition on the inside of the disk, the interior parts of the disk, if you have a big planet?
Yeah, what happens when you have a big planet it's a great question. Is that this inwards drift, it cannot pass the orbit of that giant planet. So so imagine you have your Earth-like planet on the inside, and you're supplying this kind of water-rich material inwards to that. It comes from a reservoir, like from a warehouse of ice. The size of that warehouse can only exist out to where the first giant planet is. So the farther out that giant planet is, the bigger the warehouse is. The farther in it is, the smaller it is. And we see a very important effect out of that. So you can imagine you have this very efficient conveyor belt of water inwards, and it moves stuff. There's a time at which the warehouse goes empty of water, and that time is related to how big the warehouse is. What we see in the disks is that we actually see that depletion of water. So we see a time effect. We see for relatively young disks, there's this great wet water environment with a lot of oxygen that's in the water, right? So H2O is oxygen in the water. At some point, that oxygen disappears, the water disappears, and what you have left is a carbon. And you completely change the makeup of the disk when you end up in a place where there's more carbon than oxygen, what we call the carbon to oxygen ratio. When you have more carbon to oxygen, the disk, the chemical factor of the disk switches mode, and instead of having a lot of water available, it'll have a lot of organics available. These complex organics suddenly appear. And so that changes the spectral signature. And let me see, you can find it. So here, for example, so we don't see in this case, we don't see the fingerprints of water anymore. We see these fingerprints of all these, the C and H, right, with different numbers on them, how many carbon atoms and how many hydrogen atoms you have. This is organic soup, right? Um, uh, so the planets that are forming at this late time will end up having a very, very different composition. They'll become this carbon-rich stuff instead of water-rich stuff. The time scale is having that means that there's a relation as well to the stellar mass. So turns out that planet forming disks around stars of lower mass, they evolve quicker in this way. So when we go and we look at a disk around a low mass star is much lower mass than the sun. Particular, like exactly analogous to the one that's shown here. So what is shown in the bottom. That's a TRAPPIST. Yeah. So there's that famous exoplanet system around an M dwarf star with 7 rocky planets around it, and the disk that formed these almost certainly was this very carbon-rich thing here. So the composition of those planets we predict based on this will be very, very different than what we had in our solar system. And that's because that water-rich reservoir got depleted quickly in this little disk.
So it's the size of the disk is changing the kinds of planets you've got, the materials that you have to build a planet out of. Is the star also changing the disk in a way? Like, I mean, the star for TRAPPIST-1 is a very different kind of star than our sun. How does that also go into to change the disk that you're making the planets out of?
Right. So I think so. The star will change the disk chemistry at some point. In particular, I think if you go to the very massive disk, not in the low mass, in the very massive disk, have a very harsh radiation field. So they emit a lot of ultraviolet light, and ultraviolet light breaks chemical bonds. Mm-hmm. So disks around stars that are more massive than the sun probably has a very different chemistry. When you go down to these here, we think we're really dominated by this kind of disk hydrodynamics, precipitation kind of stuff. Not so much the star itself. It's the fact that we have a relation to the size of the star is more a matter of that the disk around smaller stars is smaller. Yeah. So it's sort of a size thing.
Well, we have a question from the audience that is kind of it's a common question, I think, for any kind of public talk, which is asking about what these elements could mean about indicating life. Do you want to address kind of the topic of biosignatures and what we might look for and what biosignatures are or not?
Yeah, no, 100% right. So I can go back to that. There's you're thinking about something like the Drake equation here, right? Mm-hmm. Where which essentially is what is the probability for life? Well, it's a product of the probability of having a planet in a habitable zone, and you make life at some point during the lifetime of that planet. But the part that is often missing from that is what we call chemical habitability. So we create this modified Drake equation. Say what is the probability that you have the elements that you need for life, right? You have to have carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in order to make life as we know it. So that's the basic thing that we are looking at in terms of protoplanetary disks is we need to deliver the elements necessary for life. What happens to those elements once they're on a planetary surface in order to support life or to form it in the first place? That the chemistry happens in the planet itself, right? So it doesn't actually once you have the elements on the surface of the planet, we don't think there's any relation anymore to the molecules or the chemistry that was in the disk. The disk chemistry serves to ensure that the elements make it to the planetary surface, and then completely different things happen. And then you can talk about what are the signatures of life as we know it, which is a classical, you have oxygen along with methane, which has a chemical system out of equilibrium and things like that. But that requires, of course, for the oxygen to be there and the methane to be there, we have to have the carbon there and we have to have the oxygen there. And as we talked about, it's not obvious how you get that oxygen and carbon to the planetary surface in the first place.
So we're talking about the abundance of these elements like carbon and oxygen and nitrogen that are produced in stars, right? And we can see in other nearby galaxies like the Magellanic Clouds, they have much fewer of these elements than we have in our own solar system. They're very subsolar metallicities, right? How does that affect how planets form in those regions? Do they still form planets? Can they still have disks similar to the ones that we're seeing in the Milky Way?
It's a great question. I don't, unfortunately, don't have the answer to that
That's fine.
yet, right? Because we have to go and observe them with Webb, and very little has been done in true low metallicity regions. One reason for that is that they're still relatively distant, right? So you have to go to the, as you say, you have to go to the Mid-Atlantic clouds that are low metallicity. There are metallicity clusters in our own Milky Way. So when you go out to the outer edge of the Milky Way, those have sort of similar low metallicities, but they're still 50 to 100 times farther away than the disks that we're talking about here. So I would expect there to be quite dramatic differences, not only in the composition of planets that form, but their ability to form planets. So theorists our theorists tell us,
arguing about it, huh?
Yeah. They tell us that there will be a problem that if you go to half or a third or something like that of this amount of heavy elements that's in the sun, which is not that much. I mean, that's not an unusual thing in the universe. Then planets will have trouble forming in the disk. Whereas if you go to solar metallicity and a little bit higher, it becomes a very efficient process, and that is related to the fact that so planet formation was for a long time was really a mystery how it happens, and now we think that it happens. Certainly the formation of these planetesimals we talked about, 10, 20 miles across, that it happens through a dynamical, very unstable kind of process where the kind of drift of material that we talked about, what that does is it serves to locally enhance the amount of solids that is there, it's the amount of snow. So snow will fall down in the disk, it gets concentrated. And when you get to a certain amount of snow, you have a snowball effect. And you have this kind of collapse of material into, from things that are millimeters, a centimeter in size, all of a sudden it becomes 10 miles across, in an unstable kind of collapse.
So it reaches kind of a critical mass.
Sort of a critical mass kind of thing. And in fact, we know we have, I love this stuff. Just wanted to show this, right? So this is I'm 100% convinced. I mean, we see this evidence for this exact thing happening in our own solar system. This collapse is actually a very gentle collapse. It's not a very energetic one. So it's not like you form a star and it gets super hot and you have a nuclear furnace and stuff like that. It's sort of it's more like a floop. And so it can preserve the structure of the original grains and pebbles, we call them, that were there, that had accumulated through these drift processes. So what you have here is a condrite from our own solar systems. You slice it across, right, and you see inside. You see the structure of all these little pebbles, right? So these like millimeter-sized things, and they're surrounded by this carbonaceous stuff, right? That is called matrix. And so you can sort of imagine that you have maybe just outside the snow line, or just around, or just inside the snow line, you've had these icy pebbles that are drifting in past the snow line. So you have on the inside, you have a core of rock, right? Again, things you find on the beach, and then you have this layer of ice, and in that ice you have these organics mixed in. Where you drift inside the snow line, it gets hot enough, the water evaporates off, and you get this kind of sort of little rock with a layer of this organic stuff that hasn't evaporated. And then you have one of these gravitational events, and you flip, it all goes together, and this is what it looks like, right? And so you have this pile of rubble that have stuck together, and we see this in our own solar system. So it's difficult to see that, of course, impossible, the protoplanetary disks, but we're starting to get this picture of exactly how this happens, and we see the evidence from this process in the water spectra and molecular spectra that we see with Webb, because it tells us that this drift happens. They're icy. We see the evaporation, and we get a measure for that. We have that critical mass present just inside the snow line for this kind of very efficient formation of planetesimals, and then ultimately build up further to become an Earth.
So when we talk about like the planetesimals developing and maybe having difficulty developing in lower metallicity environments, we do have, I guess, one example of something from a low metallicity star system from our own galaxy that we just visited, right? The 3I Atlas probably came from some an older population in the Milky Way that just came by. Um, what is Webb telling us about other star systems from being able to study those kind of interstellar objects that occasionally drift by for us to
Yeah, I mean,
study?
I3 Atlas is such a fascinating. All the interstellar comets are such fascinating objects because you just heard me say that we can't. I mean, we can't see planetesimals in in other protoplanetary disks, and of course, turns out now we
There's,
can.
yeah,
Yeah,
we can
we
occasionally get
actually they
lucky.
bring them to us,
Yeah.
right? How fascinating is that? Um, and so it's right. So Webb has of course been observing an interstellar comet like I3 Atlas, and found let's say different ratios of volatile ices, carbon dioxide, and water than what we typically see in our own solar system comets, right? So we can tell from the makeup of that comet that it doesn't completely resemble the comets we have from our own solar system. And I think it tells us that um, that the the difference in chemistry that we are seeing for different protoplanetary disks with Webb seem to be translated into the different makeup in these interstellar comets. And once we have more of them, we start to get a population, start to get a broader idea, and we'll be able to match, maybe some of those comments to not to say the makeup, the structure, the circumstances of that planetary system out of which it came. So I believe that from ground-based survey observatories like Rubin, for example, we have an expectation and we'll find more, maybe many more of these interstellar comets. And I certainly hope that we'll be able to go and observe them with Webb and get a better statistics for it. I mean, it's difficult to say something right now because there's just
With so
one or
few
two,
objects.
a
Yeah.
few objects. We really need more of them. But I mean, it's fascinating that you can have this picture now of this interstellar space that is just teeming with these comets that have been ejected from their protoplanetary disks, or debris disks, long ago. And we're sort of as the sun is traveling through the galaxy, it's sort of scooping up a lot of them, and we get a chance to get this sort of sample return from
And
other
I
solar
find it
systems.
so interesting too that these things have probably always been coming through. We just haven't been able to notice them yet, and until fairly recently is the first time we've really been sensitive to being able to see them passing by. But they've been
That's
coming
right. Yeah.
by, you know, presumably regularly, and we just haven't been able to see them. Um, so looking towards the future, you talked about, with Rubin coming online, being able to see maybe more of these interstellar visitors uh, pass through our solar system and being able to study those. What other questions are you asking now that you didn't have yet to ask when Webb launched? So what questions are new in the past 4 years since Webb has started
Right.
taking
So I think
observations?
the new question is really related to this new understanding of pebble drift, this massive drift of pebble-sized objects that work to concentrate mass in the disk around where planets form. That is really the driving force, not just of the formation of planets, like it catalyzes the formation of planets, giant planet cores and planetesimals, and it sets the chemical makeup of the disk. Right, that is completely new. Um, uh, so that begs a lot of questions. To say for lower metallicity environments, we're starting to realize the limitations of Webb. So, for example, the water that we're seeing for Webb is still relatively warm. What we'd really like to see is water that. So, what we see with Webb is water that is well inside the snow line. We see water that's maybe 500 or 600 Kelvin in temperature. The snow line's at 150. So there's this big gap where we actually think where most planets are forming right around the snow line. We don't actually see that with Webb. We see things, from the conveyor a little bit later in the conveyor belt. In order to observe and measure that reservoir, how much water is there? So, what is the carbon to oxygen ratio, what is the chemistry that's happening there. We need to have access to a part of the electromagnetic spectrum that Webb doesn't have access to, namely longer wavelengths. That is where you see cooler water, and we are actually in the process of designing and hopefully build and fly an observatory that has access to those wavelengths called Prima. It is still in competition at NASA, but not for very much longer. There's an intent to make a selection soon, probably this year, and then we might be able to move forward with Prima. And that if we can do that now, I think that has the ability to perhaps even operate at the same time as Webb, and then that gives us access to not just the hot water, but all the water, and it gives us this holistic image of planet-forming chemistry.
Yeah, so not replacing Webb by any means, but working in partnership to complement one another's abilities. Then
100%, yeah. Working in partnership. It's actually using it has a lot of relation to James Webb. Like, so for example, the mid-infrared instrument on Webb that we're using to make all these measurements, it's kept very cold. It's kept colder than the James Webb telescope itself. It's
7 degrees above absolute zero. Is that?
So
Is it 7 degrees?
7 degrees above absolute zero. Miri is kept that, and it's done. It's using essentially a refrigerator to do that. So on board Webb, there's a compressor and a refrigerator that cools it down from the 50 Kelvin of the primary mirror, behind that big sun shield, down to 7 Kelvin to allow that mid-infrared instrument to operate and gives us these measurements of water. That refrigerator, when it was built for Webb, as you often do for this kind of space missions, you make a spare. Right? So in case something happens to the primary one, you can pull another one out of a box, right, and say, okay, we have a spare here. So that wasn't needed for Webb, but we're using it for Prima. So we're using it for this observatory to cool the whole thing, actually even colder than Webb, down to 4.5 Kelvin. So we have made it a little better, but it's using flight hardware that was built for Webb. So there's a direct connection between Webb and Prima. So it's one of the things that we help save some taxpayer money by being efficient this way.
Sure. It's a reduce, reuse, and recycle, right?
Reuse and recycle. The fact that you can keep the whole Prima cold down to 4.5 Kelvin instead of 50 Kelvin gives us an incredible gain in sensitivity over previous generations of this kind of what's called far-infrared observatories. If you measure relative
factor of 1 million, it looks like on that plot. Is that?
Yeah, it's about 100,000 times faster. So this is speed, right? So how much time does it take you to survey or image a part of the sky than what was done previously? The previous far-infrared missions was Sophia, which was this NASA telescope on a plane, but which was kept at room temperature, and there was Herschel, which was a European mission. So Prima would be about 100,000 times faster than those. That is close to being equivalent of if you're making an observatory on the ground for visible light, and let's say you're some alien, and you're living on a planet that has a bound rotation, right? So you have a dark side and a day side. It's like you only had access to the day side of the planet, and then you have an explorer that moves to the dark side brings their telescope, and suddenly for the first time sees the night sky. So it's that kind of difference that we can do with this. So it opens up this huge discovery space that we're very excited about. So I think we have a good case for getting this done. As you say, it is a very, very natural extension to Webb, and so you put those two together, you'll have a very, very impressive and powerful pair.
Well, that's an exciting note to, I think, conclude our discussion on and move to some audience questions. We have a few that have kind of built up. We can start to take. For one, we have here, I think, asking about that condrite collapse and the accretion of those planetesimals, asking if that collapse that is gathering those little bits together, electrostatic or gravity. is the question. I guess does it start as one and then move to the other?
Yeah, it's once you make the planetesimals, it's gravity, it's self-gravity.
Yeah.
So it overcomes any other. That's why it's so efficient, right? It overcomes any other, bounces. Right? So when people were worried about, can we even make planetesimals, they were thinking of that you had to stick things together with electrostatic forces, or how sticky are they, and if they're too fast, they'll bounce off each other, or they will break apart. But when you have a gravitational collapse of sort of the whole blob, you overcome all of that.
Yeah, the electrostatic force is so much stronger than gravity at the small scales, but it masses itself out so quickly, and gravity just keeps building and building.
Yeah.
So it eventually wins. So there's another question here. Do observations of planetary disks formations tell us anything different about dark matter as compared to observations of open space?
So the short answer is no. So the dark matter is something that operates on far, far, far larger scales, on the scales of whole galaxy clusters, right? So it's one of the properties of dark matter is from the formation of the universe. It's dark. It means it cannot cool very easily, because the way that things cool is that they radiate light away. But it's dark, so it can't do that. And in order for things to collapse, and to very small things, it has to cool. And so that's why you have these kind of dark matter is then distributed into these very, very puffy kind of things called dark matter halos around large galaxies or around whole galaxy clusters, because it can't collapse. So at the scale of a protoplanetary disk, which is many, many, many orders of magnitude smaller than that, there's no the density of dark matter there is small compared to the density of regular matter.
See, we have another question. Given that there are billions of stars in the universe, it seems more likely than not that there are planets out there which would be similar to ours. Does Webb have the capability of locating any?
So when you say planets similar to ours, you probably mean to Earth. So Webb itself is not capable, at least not with any method that I'm aware of identifying an Earth-sized planet at 1 AU around a solar mass star. So you need something else for that, and that of course is also under consideration in the form of what's called the Habitable Worlds Observatory, which is the core science case for that observatory. So you build something that is similar size to Webb, maybe a little bit bigger, but you put on it an instrument that is much better at masking out the light from the central star, and you let it operate at visible wavelengths, so a little bit shorter than Webb's wavelengths, which gives it a little bit better spatial resolution. And that has the potential to not only find Earth-like planets, but also characterize atmospheres with a spectrum. But it's very challenging to do that. It requires improvements in the precision of the mirror itself, how it's all operated, the coronagraph instrument, all those things have to be improved by 1 or 2 orders of magnitude compared to what has been demonstrated today. And so there's a tremendous amount of activity ongoing around the astronomical community to develop those technologies and demonstrate that they can be done. And once that's done, hopefully get the go-ahead to actually build an observatory, a new very large observatory that would implement that. But I think something like Habitable Worlds is required for that. If you want to characterize the Earth-like planet, if you want to know if it has an atmosphere and what it's made of. There are some other methods that were just able to find Earth-like planets like that. For example, Roman is going to make so the Roman Space Telescope is going to do that using
this year. Hopefully, we'll see.
Yeah,
but, September is as early as September, I think.
Early September it gets launched. It's using a technique called microlensing to do that. The issue with that is that due to how that technique works, any planets that it will find will be so far away that you can't follow them up and you can't measure what they made. So you get an idea how common such a thing is, like an Earth-like planet, but you wouldn't be able to pick a certain system and then go and learn something about it. You still need habitable worlds to do that.
Yeah, I've heard as Roman's going to find thousands and thousands of planets once and then never see them again, right?
Never see
That's
it.
the yeah.
That's right. But it is super. Well, listen, it's super important to know how common, because we don't know that now.
Sure.
We have no idea how common an Earth, like a true Earth analog, is, and I think that gets the gist of the question as well. So Roman would answer that, and that is a very, very important number to know for something like habitable worlds, because we shouldn't. It's not very efficient to build an observatory like habitable worlds and then realize that there aren't any. Right.
Yeah, it's kind of a question of, are you going wide and catching a whole lot of objects to understand a population, or are you going narrow and deep to find out a lot of information about a few objects, right? And Roman's kind of the wide, find out a little information about a lot of different things to build a big population of stuff.
Right.
Yeah.
Now that said, I would be very surprised if they don't find that Earth-like planets are relatively common. But we need to see. I mean, we're scientists, right? We need to go and check.
Sure, it's hard to find Earth-like planets, right?
Yeah,
I mean, if you're looking for transits, the transits are not deep and they only happen once a year, so you've got to be, looking at it for enough to see the transit happen.
Right.
So the microlensing approach that Roman has doesn't rely on that. Are there? Let's see. We have a little bit of time left for any other questions that may pop up. Are there any closing thoughts you would like to leave us with about where we stand in this moment with Webb in operation, with HWO maybe on the horizon, with Prima maybe on the horizon, with Roman about to launch?
Yeah, no, it's really is a great time for this, and I am sort of at a higher meta level as a scientist. I find it's interesting to think about what you never, like, so when you're making this, when we're learning these things, right? We're learning things every day. We're getting these amazing data, and we're having these real insights. It's always hard to imagine or to fully understand or appreciate the impact of what you're doing. If you had a time machine to go forward 10, 20, 30, 40 years, right? What does it look like, the sort of the work that we did now and the insights we had, and how did that lead to new things? But I do think that as a community in planet formation, what we're doing right now is something that's going to have this very, very lasting impact, because for the first time, we're starting to get some true insight into not only how our own planet formed, how our own solar system formed, but how all planets form, which has been a mystery for the start of, from the beginning of time, really, when people thought to think of it, but also from the beginning of my career. And I've seen this incredible evolution, and it's all enabled by building a general observatory that makes this giant leap in capability as Webb has, right? Where you have an increase in sensitivity by 100 times, or you have an increase in your spatial resolution, in your ability to image small things, again by an order of magnitude. The fact that just enables us to discover things we didn't know were there, and it demonstrates that the danger in only building observatories that exactly what they're going to find, right? You need to dare to tread these new lands without necessarily having a good idea of what you'll find. And I think this is a good example of that.
Yeah, that's a wonderful thought, that peer research is so valuable because it's unknown, because you're venturing out to this place you don't know what to expect. That's where the biggest gains are. There is a question in the chat, to close out with, about a small asteroid that broke up over Ohio yesterday. I don't know if you saw this in the news or not. I did see there was some coverage of it. No pieces were identified, but that some of the meteors and asteroids are iron rich, they know. Do those come from the collisions that we've been talking about that happen after planet formation? Is that thing that just came in over Ohio left over from this process we were talking about?
Yeah. So I did see that briefly. It's fascinating. I love these things. Yes, it almost certainly comes from a collision, especially if it's an iron meteorite. Because if it's iron nickel rich, right, so then that meteorite has come from a molten core, right, where you've actually created a planetesimal that's big enough that has heated its interior by enough that it melted. And that only happens when you have something that's quite large. And so in order for it to, I think this was a few feet across or something like that, the one in Ohio, something, it was pretty big. But still, I mean, to get a chunk of iron that is that small, it would have had to been broken up at some point. So that has been very, very common in the past, that you break up planetesimals like that.
Well, thank you very much. I think we have just a quick closing, that I would like to remind everybody just to, again, subscribe to our channel so you can see updates that come out from new videos or new events that we have. Our next Deep Space Dialogue event is going to be in May, so keep an eye out for that. And I just wanted to give a thank you to everyone behind the scenes on our team that puts in so much effort to make these happen. Ralph, if you want to come on screen to say hi, take a bow for all the work that you do behind the scenes.
Hello.
Making sure that our connection is good and going out to the world. And then also Zena, our designer that puts together our nice templates, and Quinn Hart, who's leading the communications portfolio for Web out of STSCI. So thank you to everyone on the team, and thank you all to the audience who took time out to come listen to us talk to each other and ask your excellent questions. And big thank you to Klaus for spending his time with us this evening.
Thanks so much for having me on.
Okay. Thank you all, and have a wonderful night.